You think space is empty. You think it's nothing, a void, a gap between things, the absence of matter. But Richard Feynman, one of the greatest physicists who ever lived, told us something that should terrify you. Space isn't empty. It's never been empty. And what's happening in the space around you right now, in the gap between your screen and your eyes, is so violent, so chaotic, so utterly bizarre, that if you could see it, you would lose your mind. Let me show you what I mean. Hold your hand up in front of your face. Look at the space between your hand and your face. What do you see? Nothing, right? Empty space. Air, maybe, if you want to be technical. Molecules bouncing around. But mostly nothing. That's what your eyes tell you. That's what your brain believes. But here's what Feynman discovered. That space, that supposedly empty space, is boiling. It's seething with activity. Particles are appearing and disappearing. Energy is fluctuating wildly. The vacuum itself is alive, writhing, constantly creating and destroying matter in a frenzy that never stops. This isn't metaphor. This isn't poetic language. This is what quantum mechanics tells us is actually happening right now, in the space you think is empty. And Feynman was the one who figured out how to calculate it, how to prove it, how to show that the vacuum is anything but empty. He called them virtual particles, and they're everywhere. Popping into existence, existing for the briefest instant allowed by the laws of physics, then vanishing back into nothingness. Electron-positron pairs, photons, quarks, an entire zoo of particles constantly being created and annihilated in the space around you. Now, you might be thinking, okay, but if I can't see them, if they disappear so fast, do they even matter? Are they even real? And here's where Feynman's genius comes in. He showed us that these virtual particles aren't just theoretical curiosities. They have real, measurable effects. They change the behavior of actual particles. They affect the strength of electromagnetic fields. They even change the mass of electrons. We can measure these effects in laboratories. We've tested them to incredible precision. And the experiments match Feynman's predictions exactly. Let me tell you what this means. It means that an electron, a simple fundamental particle, isn't actually simple at all. It's constantly surrounded by a cloud of virtual particles, photons appearing and disappearing, electron-positron pairs flashing in and out of existence. The electron is swimming in a sea of quantum fluctuations. And those fluctuations change everything about how the electron behaves. Feynman developed a way to visualize this. He created diagrams, simple pictures that represent these quantum processes. You've probably seen them. Little lines and vertices showing particles interacting, being created, being destroyed. They're called Feynman diagrams, and they revolutionized physics. But here's what most people don't understand about Feynman diagrams. They're not just pictures. They're calculations. Each diagram represents a mathematical expression. And when you add up all the diagrams, all the possible ways particles can interact, you get predictions. Predictions about how particles behave. Predictions that can be tested. And when physicists tested them, the predictions were right. Absurdly right. Right to 10 decimal places. Right to a precision that beggars belief. The most famous example is the magnetic moment of the electron. Classical physics predicted one value. Experiments measured a slightly different value. Feynman's quantum electrodynamics, his theory of how light and matter interact, explained the difference. The virtual particles, the quantum fluctuations, the seething activity of empty space, they all contributed to making the electron's magnetic moment slightly different than the classical prediction. And when physicists calculated the contribution from virtual particles using Feynman's methods, it matched the experiments perfectly. This is real. This is not speculation. Now watch this, because it gets stranger. Those virtual particles I told you about, the ones appearing and disappearing in empty space, they're actually violating one of the most sacred laws of physics: conservation of energy. Energy cannot be created or destroyed, right? That's what you learned in school. That's one of the fundamental rules. But virtual particles are creating energy out of nothing. They're appearing without borrowing energy from anywhere. They're breaking the rules.
How is this possible? Feynman explained it using Heisenberg's uncertainty principle.
One of the deepest results in quantum mechanics. The uncertainty principle tells us that there are limits to what we can know about a particle. Specifically, you cannot know both the exact position and the exact momentum of a particle at the same time. The more precisely you know one, the less precisely you can know the other. This isn't about measurement limitations. This isn't about our technology not being good enough. This is a fundamental property of reality itself. But there's another version of the uncertainty principle that most people don't know about: the energy-time uncertainty principle. It says that if you look at a very short period of time, energy doesn't have to be conserved. The shorter the time interval, the bigger the energy fluctuation you can have. And here's the key: virtual particles exist for such incredibly short times that they can borrow enormous amounts of energy from the vacuum, use that energy to exist briefly, then disappear before the universe notices. The universe allows this. The laws of quantum mechanics permit it. Let me give you the numbers so you understand how extreme this is. The lifetime of a virtual particle is roughly related to its mass by Heisenberg's uncertainty principle. A virtual electron-positron pair, for example, might exist for about 10 to the minus 21 seconds. That's 0.00000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000seconds, a trillionth of a trillionth of a second. In that time, the particles can travel about 10 to the minus 13 meters before they annihilate. That's roughly the size of an atomic nucleus. They don't go far. They don't last long. But they're real enough to affect everything around them. And here's what Feynman realized. If you want to calculate what happens when an electron moves from point A to point B, you can't just consider the direct path. You have to consider all possible paths, including paths where the electron emits a virtual photon, which then creates a virtual electron-positron pair, which then annihilates, which then creates another photon, and so on. Every possible sequence of virtual particle creation and annihilation has to be included in the calculation. And when you add them all up using Feynman's rules, you get the right answer. The answer that matches experiments. This is called the path integral formulation of quantum mechanics, and it's one of Feynman's greatest contributions to physics. The idea is simple but profound. A particle traveling from one point to another takes every possible path simultaneously, not just the straight line, not just a few alternatives. Every single path, no matter how crazy, no matter how convoluted, contributes to the particle's behavior. And the way you calculate the final result is by adding up the contribution from every path, weighted by a quantum probability amplitude. Now, you might be thinking, wait, if particles take every possible path, why do we only see them going in straight lines? Why doesn't a thrown ball suddenly veer off to the side or loop around? And this is where Feynman's brilliance really shines. Most of those crazy paths cancel out. The quantum amplitudes interfere with each other. Paths that are wildly different from the classical trajectory have amplitudes that oscillate rapidly, and when you add them up, they destroy each other. Only paths close to the classical path survive the cancellation. That's why large objects behave classically. The quantum weirdness is still there, but it cancels itself out. But for small particles, for electrons and photons, the quantum paths matter, the virtual particles matter. The fluctuations of empty space matter. And Feynman gave us the tools to calculate it all. Here's something that should blow your mind. The vacuum, the supposedly empty space, has energy. Lots of energy. In fact, according to quantum field theory, the vacuum energy should be infinite. Every point in space should have an infinite amount of energy because there are infinite possible virtual particles that can appear at every point. This is called the vacuum catastrophe, and it's one of the biggest unsolved problems in physics. Now, obviously the vacuum doesn't have infinite energy. We would notice if it did. The universe would be very different. So what's going on? Physicists solve this problem by a trick called renormalization. They subtract away the infinity, essentially setting the 0 point of energy to whatever the vacuum energy actually is. This works. It gives finite answers that match experiments. But it's deeply unsatisfying. We're essentially saying, we don't know what the vacuum energy is, so we'll just measure it and define that to be 0. It feels like sweeping a problem under the rug. But here's the terrifying part. Even after renormalization, even after we subtract away the infinity, there should still be a finite vacuum energy left over, and that energy should affect the universe. Specifically, it should cause empty space to push outward, to drive the expansion of the universe. This is called the cosmological constant, and Einstein actually proposed it long before quantum mechanics. He later called it his greatest blunder. But here's the thing. We've measured the expansion of the universe, and it is accelerating. Empty space does seem to have energy. We call it dark energy. The problem? The vacuum energy predicted by quantum field theory is about 10 to the power of 120 times larger than the dark energy we actually observe. That's not a typo. That's a 1 followed by 120 zeros. This is the worst prediction in the history of physics, off by a factor so large it's almost incomprehensible. And we have no idea why. Feynman himself knew about this problem. He knew that quantum field theory predicted absurd values for the vacuum energy, and it bothered him. It bothered him deeply. Let me tell you what Feynman said about this. He was brutally honest about what we don't know. He didn't pretend to have answers. He didn't have. He said, and I'm paraphrasing here, that nature's imagination is far greater than man's, that we should never assume we've figured everything out, that the universe is under no obligation to make sense to us. And the vacuum energy problem is a perfect example. We have a theory, quantum field theory, that works incredibly well. It predicts the magnetic moment of the electron to 10 decimal places. It explains the behavior of particles in accelerators. It's the most successful theory in the history of science. And yet, it gives completely wrong answers for the vacuum energy. Something is missing. Something fundamental. Now, let's talk about another terrifying aspect of space that Feynman explored. The fact that particles don't have definite positions. You think a particle is a little ball, a tiny object sitting at a specific location. But that's not what quantum mechanics tells us. A particle, according to quantum mechanics, is described by a wave function, and that wave function is spread out over space. The particle is, in some sense, in multiple places at once. Only when you measure it, only when you interact with it, does it suddenly have a definite position. Feynman had a brilliant way of thinking about this. He said, don't ask where the particle is before you measure it. That question doesn't have an answer. The particle doesn't have a position until you measure it. It's not that we don't know where it is. It's that it genuinely isn't anywhere specific. It's in a superposition, existing in multiple places simultaneously, and only when you measure it does the wave function collapse and the particle suddenly appears at one location. This is deeply weird. This violates every intuition we have about how reality works. But it's been tested over and over and over. The double-slit experiment is the classic demonstration. Send electrons through two slits and they create an interference pattern. An interference pattern means the electrons are going through both slits simultaneously, like waves. But if you measure which slit the electron goes through, the interference pattern disappears. The electron suddenly behaves like it went through just one slit. Measurement changes reality. Feynman called this the central mystery of quantum mechanics, the fact that observation affects what's being observed, not in a trivial way, like shining light on something and disturbing it, but in a fundamental way. The act of measurement creates the property being measured. Before measurement, the particle doesn't have a position. After measurement, it does. The universe is stranger than we ever imagined. And here's where it gets truly terrifying. If particles don't have definite positions, then space itself becomes ambiguous. What does it mean to say something is located in space if location isn't a definite property? What is space if it's not a container for objects with definite positions? Feynman pushed on these questions. He asked, what is space really? Is it just a mathematical abstraction, a coordinate system we use to describe relationships between events? Or is it a real thing, a physical entity? The answer, according to quantum field theory, is that space is a field. Actually, space is many fields. There's an electromagnetic field filling all of space. There's an electron field filling all of space. There are quark fields and gluon fields and neutrino fields, all of them filling every point in space simultaneously. And what we call particles are actually excitations of these fields. An electron isn't a little ball. It's a ripple in the electron field. A photon is a ripple in the electromagnetic field. Space isn't empty because it's full of fields, and those fields are constantly fluctuating, constantly creating virtual particles, constantly seething with activity. Feynman developed the mathematical tools to deal with these field fluctuations. His diagrams represent interactions between field excitations. His path integrals sum over all possible field configurations. And his renormalization techniques allow us to extract finite, meaningful predictions from equations that would otherwise give infinite nonsense. This framework, quantum field theory, is the foundation of modern particle physics. It's how we understand the Standard Model. It's how we predicted the Higgs boson. It's how we calculate what happens in particle colliders. But Feynman also knew the limits of quantum field theory. He knew it doesn't include gravity. He knew it breaks down at extremely short distances. He knew that if you try to probe space at distances smaller than the Planck length, about 10 to the minus 35 meters, the theory stops making sense. At those scales, quantum fluctuations of space itself become important. Space-time itself starts to fluctuate. The smooth fabric of space that we assume exists might dissolve into a foaming, bubbling quantum chaos. This is called quantum foam, or space-time foam. It's a speculative idea, but it follows naturally from combining quantum mechanics and general relativity. If matter creates virtual particles through quantum fluctuations, then mass energy creates virtual black holes through gravitational fluctuations. Tiny black holes, smaller than atoms, appearing and disappearing in the vacuum. Space-time itself tearing and reconnecting, the very fabric of reality becoming unstable at the smallest scales. Feynman was fascinated by this idea, but also frustrated. We don't have a complete theory of quantum gravity. We can't calculate what happens at the Planck scale. It's one of the great unsolved problems in physics. Let me tell you something else Feynman said that's haunting. He said that nobody understands quantum mechanics. Not even him. Not even the experts. We have the equations. We can make predictions. We can test them and find they're correct. But we don't really understand what's happening. We don't have an intuitive grasp of why particles behave the way they do. We just know that the math works. This is deeply unsatisfying. We want understanding, not just calculation. But the universe doesn't care what we want. Here's an example of how weird things get. Entanglement. Feynman worked on this too. Two particles can become entangled, connected in such a way that measuring one instantly affects the other, no matter how far apart they are. This isn't science fiction. This is observed in laboratories every day. It's the basis for quantum computing and quantum cryptography. But it's bizarre. How can two particles separated by light years be connected? How can measuring one instantly change the other? Einstein hated this. He called it spooky action at a distance. He thought it proved quantum mechanics was incomplete, that there must be hidden variables we don't know about. But experiments have proven Einstein wrong. Entanglement is real. The correlations between entangled particles are stronger than anything classical physics allows. And there are no hidden variables. The particles genuinely don't have definite properties until measured, and yet they're connected. Feynman accepted this. He didn't like it, but he accepted it. He said, "The way nature actually works is much more complicated than our common sense intuition suggests. Particles are entangled. The vacuum is full of virtual particles. Space is made of fluctuating fields. These aren't problems with the theory. These are features of reality, and we have to accept them, even if we don't understand them." Now watch this. There's another aspect of space that Feynman explored that's even more disturbing. The arrow of time. You think time flows forward, past to present to future. That's obvious, right? You remember the past, you experience the present. The future hasn't happened yet. But here's the thing. The fundamental laws of physics don't care about the direction of time. Newton's laws work the same forwards and backwards. Maxwell's equations work the same forwards and backwards. Even Einstein's general relativity works the same forwards and backwards. If you film a planet orbiting a star and play it backwards, you can't tell. The physics looks the same. But clearly, time does have a direction. Eggs break, but don't unbreak. Milk mixes into coffee, but doesn't unmix. People age, but don't get younger. There's an arrow of time in our everyday experience. So where does it come from? Feynman worked on this problem. The answer has to do with entropy, with disorder. The second law of thermodynamics says that entropy always increases. Disorder always grows. And that's what gives time its direction. The future is the direction of increasing entropy. But here's the disturbing part. At the microscopic level, at the level of individual particles, there's no arrow of time. An electron scattering off a photon looks the same forwards and backwards. The arrow of time only emerges when you have many particles, when you have statistical behavior. It's not a fundamental law. It's a statistical tendency. And that means, in principle, entropy could decrease, eggs could unbreak, milk could unmix. It's just incredibly unlikely. Feynman showed that you can run quantum mechanics backwards in time. You can take a final state and calculate what initial state it came from. The equations work both ways. Time reversal symmetry. The laws of quantum mechanics don't prefer one direction of time over another. And yet, we experience time flowing in one direction. Why? We don't fully know. This is another deep mystery that Feynman grappled with, but didn't solve. Here's something else that should terrify you. Quantum mechanics tells us that the future isn't determined. Not just unknown, but actually undetermined. When an electron is in a superposition of two positions, it doesn't have a definite position. And when you measure it, the result is random, genuinely random. Not pseudo-random like a coin flip, where the outcome is determined by initial conditions we don't know. Actually random. The universe is fundamentally probabilistic. Einstein hated this too. He famously said, "God does not play dice." He believed there must be some underlying determinism, some hidden mechanism that determines outcomes. But Feynman, following the Copenhagen interpretation, said no. Randomness is fundamental. When a radioactive atom decays, there's no cause. It just happens. Spontaneously. Randomly. The universe genuinely has randomness built into it at the deepest level. This is terrifying because it means the future is open. Not just unknown, but undecided. The universe is creating itself moment by moment through quantum randomness. Every measurement, every interaction, every quantum event is making a choice that wasn't determined beforehand. We live in a universe that's improvising as it goes, and there's nothing beneath it. No deeper level where things are deterministic. The randomness is bedrock. Let me tell you about another Feynman idea that's deeply strange. Antimatter. Every particle has an antiparticle. An electron has a positron. A proton has an antiproton. When matter and antimatter meet, they annihilate, converting their mass entirely into energy. This is real. This happens in particle accelerators. This is how PET scanners work in hospitals. But here's the weird part. Feynman realized you can think of antimatter as matter going backwards in time. Imagine an electron moving forward in time. Now imagine that electron absorbs a photon and reverses direction in time. From our perspective, watching time move forward, we see the electron absorb a photon and then see a positron appear and move away. The positron is the electron going backwards in time. This isn't just a mathematical trick. This is a legitimate way to interpret the equations, and it leads to strange conclusions. For instance, it means that all electrons might actually be the same electron, moving backwards and forwards through time, threading through history. Every electron in your body, every electron in a star, could be the same particle, just at different points in its timeline. Feynman himself didn't believe this literally, but he found it fascinating that the math allowed it. The equations of quantum field theory don't care about the direction of time. Particles and antiparticles are related by time reversal. Reality is stranger than we can imagine. Now, let me address something that might be bothering you. If space is full of virtual particles, if the vacuum is seething with activity, why don't we notice it? Why does space seem empty? The answer is about scales. The quantum fluctuations happen at incredibly small distances and incredibly short times. They average out. When you look at space on human scales, on the scale of meters and seconds, all the quantum chaos averages to smooth, empty vacuum. It's like looking at a calm ocean from an airplane. It looks smooth and flat. But if you were the size of a molecule sitting on the surface, you'd see a violent, turbulent mess of water molecules colliding. We're like that airplane observer. We see smooth space because we're big. But if you could shrink down to the Planck scale, if you could see distances of 10 to the minus 35 meters and times of 10 to the minus 43 seconds, you would see the quantum foam. You would see space-time itself fluctuating wildly, tearing and reconnecting, frothing with virtual particles and quantum uncertainty. And you would lose your mind, because nothing about it would make sense to your evolved, classical intuition. Feynman understood this. He understood that our brains evolved to understand the macroscopic world. Throwing rocks, finding food, avoiding predators. We did not evolve to understand quantum mechanics. So it's not surprising that quantum mechanics feels wrong. It should feel wrong. What would be surprising is if the fundamental nature of reality matched our intuitions. The fact that it doesn't tells us something important. The universe is not built for our comprehension. We have to work to understand it. We have to override our intuitions and trust the math. Here's another thing Feynman emphasized. Quantum mechanics forces us to give up classical pictures. You cannot visualize what's really happening. You cannot imagine a particle as a little ball with a definite position and velocity. That picture is wrong. The particle is described by a wave function, and the wave function doesn't correspond to anything you can visualize. It's a complex valued function over configuration space. It's not a wave in real space. It's not an object. It's a mathematical description of probability amplitudes. And that's all we have. This is why Feynman said, if you think you understand quantum mechanics, you don't understand quantum mechanics. The moment you think you have an intuitive grasp, you've probably fooled yourself. The best we can do is shut up and calculate. Use the equations, make predictions, test them. But don't ask what's really happening, because that question doesn't have an answer we can understand. And yet, despite this, Feynman made incredible progress. He developed new ways to calculate quantum processes. He invented new mathematical tools. He made predictions that were tested and confirmed. He showed that even though we don't understand quantum mechanics intuitively, we can still use it. We can still extract knowledge from it. We can still make progress. Understanding and calculation are not the same thing. We can calculate without understanding. And sometimes that's the best we can do. Let me bring this back to the main point. Space is not what you think it is. It's not empty. It's not a passive container. It's not a fixed stage where events happen. Space is an active, dynamic quantum field. It's constantly fluctuating. It's full of virtual particles. It's entangled with matter. It has energy. It curves and warps. It might even be discrete at the smallest scales, made of tiny, indivisible chunks of space-time. We don't know. We're still figuring it out. And here's what's truly terrifying. The more we learn about space, the less familiar it becomes. Every answer raises new questions. Every solution reveals new mysteries. The vacuum energy problem, the nature of dark energy, the structure of space-time at the Planck scale, the origin of the arrow of time, the interpretation of quantum mechanics. These are open questions. These are things we don't understand, and they're fundamental. They're about the nature of reality itself. Feynman embraced this uncertainty. He didn't pretend to have answers he didn't have. He didn't sweep problems under the rug. He confronted them honestly. He said, look, we don't know. We have equations that work, but we don't know why they work. We have theories that make predictions, but they lead to absurdities like infinite vacuum energy. Something is missing. And he was okay with that. He was comfortable with uncertainty. This is the opposite of how most people think about science. Most people think science gives us certainty, final answers, definitive truths. But that's not how it works. Science gives us better and better approximations, more and more accurate models, deeper and deeper understanding. But there's always more to learn, always new questions, always mysteries at the frontier. And the mysteries don't get easier. They get harder, because we've already figured out the easy stuff. The nature of space is one of these deep mysteries. We know it's not empty. We know it's quantum. We know it's a field. We know it fluctuates, but we don't know what it is made of. We don't know if space is fundamental or emergent. We don't know if space-time is continuous or discrete. We don't know how to combine quantum mechanics and general relativity into a single theory. These are some of the biggest open questions in physics, and they're questions about space itself. Here's what Feynman would tell you. Don't be satisfied with simple answers. Don't accept explanations that make you comfortable. Push deeper. Ask harder questions. Demand evidence. Test predictions. And be willing to accept that reality is stranger than you imagined. The universe doesn't owe you intuitive understanding. It doesn't care if quantum mechanics makes sense to you. It just is what it is. And our job as thinking beings is to figure it out, even if it takes centuries, even if it requires us to abandon cherished assumptions, even if it leaves us bewildered. Now, watch this. There's one more aspect of space that Feynman explored that I need to tell you about: the relationship between space and information. In quantum mechanics, information is physical. You can't copy quantum information perfectly. This is called the no-cloning theorem. You can't measure a quantum state without disturbing it. This is fundamental, and it has consequences for space itself. Black holes are the perfect example. When something falls into a black hole, where does the information go? Does it disappear? That would violate quantum mechanics, which says information is conserved. Does it escape somehow? That seems impossible because nothing can escape a black hole. This is called the black hole information paradox, and it's one of the deepest problems in theoretical physics. And it's a problem about space, about what happens to space-time inside a black hole, about whether information is stored on the event horizon, about whether space itself is holographic, with all the information about a three-dimensional volume encoded on its two-dimensional boundary. Feynman didn't solve this problem. It came to prominence after his death. But he laid the groundwork. He showed us that quantum mechanics and space-time are intimately connected, that you can't understand one without the other, that information, physics, and geometry are all part of the same structure, and that structure is reality itself. Let me tell you something personal. When I study Feynman's work, when I read his lectures and his papers, what strikes me most is his honesty. He didn't oversell his understanding. He didn't pretend physics had all the answers. He said, here's what we know, here's what we don't know, here's what we're confused about. And he invited everyone to join the adventure of figuring it out. He didn't mystify. He didn't obscure. He explained things as clearly as possible while acknowledging where clarity ended and mystery began. And the mystery of space is profound. We live in it. We move through it. We measure it. We use it in our calculations. But we don't really know what it is. Is it a thing or a relationship? Is it fundamental or emergent? Is it continuous or discrete? These aren't just academic questions. These are questions about the nature of existence itself, about what it means for something to be somewhere, about what reality is made of at the deepest level. Here's the truth. Space might be finite or infinite. It might be flat or curved. It might be continuous or discrete. It might be fundamental or emergent, from something more basic. We don't know. What we do know is that space is quantum. It fluctuates. It's full of fields. It's connected to time. It's affected by matter and energy. It's far more complex and strange than the empty container our intuition suggests. And every time we probe deeper, we find new surprises, new phenomena that don't fit our expectations, new questions that don't have obvious answers. Feynman taught us to be comfortable with this, to embrace the uncertainty, to enjoy the mystery, to find beauty in the questions themselves, not just in the answers, because the questions are what drive us forward. The questions are what make science exciting. The questions are what separate knowledge from mere belief. And the deepest questions are about space and time, and matter and energy, about the fundamental fabric of reality, about what everything is made of and how it all fits together. So, what is space? According to Feynman, according to quantum field theory, according to everything we've learned from experiments and calculations, space is a quantum field, or rather many quantum fields, all vibrating, all fluctuating, all creating virtual particles, all interacting with matter, all affecting and being affected by the contents of the universe. Space is active, space is dynamic, space is quantum, and space is deeply, fundamentally, terrifyingly strange. And here's the beautiful part. We figured this out. Creatures made of atoms, living on a small planet, using mathematics and experiments, discovered the quantum nature of space. We can't see it directly. We can't experience it intuitively. But we deduced it through careful reasoning and measurement. We built particle accelerators and measured electron magnetic moments to 10 decimal places. We detected virtual particles through their effects on real particles. We tested quantum field theory thousands of times and found it correct every time. We know space is quantum because we measured it. That's the power of physics. Not just collecting facts, but understanding structure. Understanding what questions to ask. Understanding how to test ideas. Understanding that reality is mathematical at its core and that math can reveal truths that intuition cannot. Feynman was a master of this. He could calculate anything. He could take any physical process and find a way to compute it using his diagrams, his path integrals, his techniques, and the calculations worked. They gave right answers. They predicted new phenomena. They explained puzzles. But Feynman never lost sight of the fact that calculation isn't understanding. That we still don't know what quantum mechanics means. That the wave function is still mysterious. That the measurement is still weird. That entanglement is still spooky. That virtual particles are still bizarre. These aren't failures of the theory. These are features of reality. And they tell us that reality is far stranger than common sense suggests. Let me leave you with this. The next time you look at empty space, remember what's really there. Virtual particles appearing and disappearing. Quantum fields fluctuating. Energy borrowed from the vacuum. The space-time fabric itself vibrating at the smallest scales. None of it visible. None of it intuitive. All of it real. All of it tested. All of it confirmed by experiment. Space is not empty. It never was. And Feynman showed us how to calculate it, how to predict it, how to test it. He gave us the tools to understand the quantum vacuum, and what we found is terrifying and beautiful and utterly unlike anything our ancestors imagined. This is the universe we live in, a universe where space is quantum, where particles are fields, where vacuum is full, where time can run backwards, where information is physical, where randomness is fundamental, where nothing makes intuitive sense, but everything makes mathematical sense. And we have Richard Feynman to thank for showing us how to navigate this strange reality, for giving us the diagrams and the integrals and the techniques to calculate what happens in this quantum universe, for being honest about what we don't understand, for inviting us to join the adventure. Space isn't what you think it is. It's stranger. It's quantum. It's active. It's full. And it's terrifying in the best possible way. Because it means reality is far richer and far more mysterious than we ever imagined. And we're only beginning to understand it. Now, let me tell you about one final aspect of Feynman's work that brings everything together. The Lamb shift. This was one of the first experimental confirmations that virtual particles are real, that the quantum vacuum has real measurable effects. And Feynman's calculation of it was a triumph. Let me explain what it is and why it matters. In the 1940s, physicists discovered something strange. Electrons in hydrogen atoms don't have exactly the energies that simple quantum mechanics predicts. There's a tiny difference, a shift in energy levels that shouldn't be there, according to Dirac's equation. This shift was measured by Willis Lamb, and it was a puzzle. What was causing it? The answer is virtual particles. The electron in the hydrogen atom is constantly surrounded by a cloud of virtual photons. These photons appear and disappear, and they affect the electron's energy. They change how the electron interacts with the proton. They modify the electromagnetic field, and this modification shifts the energy levels slightly. Feynman calculated this shift using his diagrams and his techniques. He considered all the ways virtual photons could be created and absorbed by the electron. He added up all the contributions, and he got a number that matched the experimental measurement. This was huge. This was proof that virtual particles aren't just mathematical abstractions. They have real effects. You can measure them. The Lamb shift is about 1000 megahertz, a tiny energy compared to the overall binding energy of the electron. But it's measurable, and it matches Feynman's prediction. What does this tell us? It tells us that the vacuum, the supposedly empty space between the electron and the proton, is full of virtual photons. And those photons matter. They change the physics. They affect real particles. The vacuum is not empty. It's an active participant in every physical process. And we can calculate its effects using quantum field theory. This is not speculation. This is measured fact. The space around you, right now, is full of virtual particles affecting everything that happens. Here's another example, the Casimir effect. If you take two uncharged metal plates and put them very close together in a vacuum, they attract each other. Why? Because the vacuum between the plates is different from the vacuum outside. The metal plates restrict which virtual photons can exist between them. Only photons with certain wavelengths fit in the gap, but outside the plates, all wavelengths of virtual photons can exist. This creates an imbalance. There's more vacuum energy outside the plates than between them, and this energy difference creates a force that pushes the plates together. This has been measured. This is real. You can feel the force of virtual particles if you set up the experiment right. The Casimir force is weak, but it's definitely there, and it's caused by the quantum fluctuations of empty space. Again, space is not empty. It's full of fields that fluctuate, and those fluctuations create measurable forces. Feynman didn't work on the Casimir effect directly, but it's a consequence of the same quantum field theory he helped develop. It's more evidence that the vacuum is alive with quantum activity. Now here's something that should really disturb you. The uncertainty principle applies to everything, including fields. That means electromagnetic fields fluctuate randomly. Even in empty space, even with no particles around, the electric field and magnetic field at any point are constantly changing, fluctuating around zero. You can't have a perfectly zero field, because that would violate the uncertainty principle. You can't know both the field value and its rate of change exactly, so the field must fluctuate. These are called zero-point fluctuations, and they're everywhere. Every point in space, every moment in time, fields are randomly fluctuating, and this is not avoidable. It's not a limitation of our technology, it's a fundamental property of quantum fields. These zero-point fluctuations contribute to the vacuum energy problem I mentioned earlier. Every mode of every field has a zero-point energy of half a quantum, and there are infinitely many modes. So the total zero-point energy is infinite. This is the vacuum catastrophe. We deal with it by renormalization, by subtracting infinity and redefining zero. But it's unsatisfying. We're essentially saying we don't understand the vacuum energy, so we'll just set it to whatever we measure it to be. This works for calculations, but it doesn't feel like real understanding. Feynman was very aware of this. He knew that quantum field theory has infinities built into it. He knew that renormalization is a trick, not an explanation. But he also knew that the trick works. It gives right answers, and sometimes that's all you can ask for. Physics is not about philosophical satisfaction. It's about making predictions that match experiments. And quantum field theory does that incredibly well. The infinities are annoying, but they're manageable. We can work around them, and the predictions we get are fantastically accurate. Let me give you another example of how accurate these predictions are. The anomalous magnetic moment of the muon. The muon is like a heavy electron. It's unstable and decays quickly, but while it exists, it has a magnetic moment. And that magnetic moment is affected by virtual particles, just like the electron. Physicists have measured the muon's magnetic moment to incredible precision, and they've calculated it using quantum field theory including contributions from virtual particles of all types. The agreement is stunning. Theory and experiment match to 9 decimal places. This is one of the most precise tests of quantum field theory ever performed. But here's the interesting part. Recent measurements suggest there might be a tiny discrepancy. The measured value might be slightly different from the predicted value. If this holds up, if the discrepancy is real, it could mean there are new particles we haven't discovered yet, virtual particles that we haven't included in the calculation. This is exciting. This is how new physics gets discovered. You make a precise measurement, you compare it to a precise calculation, and if they don't match, something new is going on. This is the frontier. This is where Feynman's methods are still being used today to search for new phenomena. Think about what this means. The quantum vacuum, the fluctuating fields, the virtual particles. They're not just theoretical ideas. They're tools for discovery. By calculating their effects very precisely and comparing to experiments, we can detect new physics. We can find particles that don't exist in our current theories. The vacuum is a laboratory. It's constantly creating every possible particle allowed by the laws of physics. And if there are particles we don't know about, they'll show up as tiny discrepancies in measurements. This is how we explore the unknown. Not by building bigger machines, though that helps, but by being more precise, by calculating more carefully, by testing theory against experiment at higher and higher levels of accuracy. Feynman would have loved this. He loved precision. He loved calculation. He loved finding discrepancies and figuring out what they meant. He once said that science is a process of comparing what we predict to what we measure. And when they disagree, that's when things get interesting. That's when we learn something new. And the muon magnetic moment might be one of those cases. We'll see. Now, let me address something about Feynman himself, because his personality shaped how he thought about physics. He was irreverent. He didn't care about authority or tradition. He questioned everything. He insisted on understanding things his own way, in his own language. And this led him to develop new methods that nobody else had thought of. The Feynman diagrams, for example, were initially controversial. Other physicists didn't trust them. They seemed too simple, too pictorial. How could little drawings capture the complexity of quantum field theory? But Feynman knew what he was doing. He had worked out the mathematics behind the diagrams. Each line, each vertex, corresponded to a precise mathematical expression. The diagrams were a tool for organizing calculations, for keeping track of all the terms. And they worked. They gave right answers faster than the traditional methods. Eventually, everyone adopted them. Now, you can't do particle physics without Feynman diagrams. They're standard. They're in every textbook. They're how physicists think about particle interactions. And it all started because Feynman refused to do things the way everyone else did. This is a lesson about creativity in science. You don't have to follow the established methods. You don't have to think like everyone else. If you understand the physics deeply enough, you can invent your own tools. You can find new ways to approach problems. Feynman did this repeatedly throughout his career. He invented new techniques, new mathematical methods, new ways of thinking, and many of them became standard tools that everyone uses. His path integrals, his parton model of protons, his quantum computing ideas, all of them were initially unconventional. All of them are now mainstream. And here's what's terrifying about this. It means we might be missing things. If the next breakthrough requires thinking in a completely new way, using tools we haven't invented yet, then we won't find it until someone has Feynman's level of creativity and insight. We might be stuck. We might be staring at the data, at the equations, at the experiments, and not seeing the answer because we're thinking in the old way. This has happened before. It'll happen again. And the only solution is to encourage more people to think creatively, to question assumptions, to try new approaches, just like Feynman did. Let me tell you one more thing about the nature of space that Feynman understood deeply. Symmetry. The laws of physics have symmetries. If you rotate space, the laws don't change. If you shift position, the laws don't change. If you reflect space, like in a mirror, most laws don't change. These symmetries are fundamental, and they have consequences. There's a deep theorem, Noether's theorem, that says every symmetry corresponds to a conservation law. Symmetry under time translation gives us conservation of energy. Symmetry under space translation gives us conservation of momentum. Symmetry under rotation gives us conservation of angular momentum. Feynman knew this and used it constantly. Symmetries constrain what can happen. They limit the possible interactions. They make calculations easier. If you know a process must conserve some quantity because of a symmetry, you can rule out many possible diagrams, many possible outcomes. Symmetry is a powerful tool, and it's built into the structure of space-time itself. The fact that space is the same everywhere, that it's the same in every direction, that it doesn't change with time, these facts have profound physical consequences. They ensure that energy and momentum are conserved. They ensure that experiments done here give the same results as experiments done somewhere else. They make physics possible. But here's the strange part. Some symmetries are broken. The universe is not perfectly symmetric. Matter and antimatter, for example, should be symmetric. Every particle has an antiparticle. The laws treat them the same. But the universe is made of matter, not antimatter. Why? This asymmetry is still not fully explained. It's called the baryon asymmetry problem, and it's one of the great mysteries. Somehow, in the early universe, slightly more matter than antimatter was created. And when matter and antimatter annihilated, a tiny excess of matter remained. That excess is everything we see. All the stars, all the galaxies, all the atoms in your body. They're the leftovers from an asymmetry we don't fully understand. Feynman worked on problems like this. He tried to understand why the universe is the way it is, why these particular symmetries, why these particular laws. And often he didn't find complete answers. But he found better questions. He found new ways to think about old problems, and that's just as valuable. Because science progresses by asking better questions, not just by finding answers. Here's the deep truth that Feynman taught us. Space is not a background, it's not a stage, it's not a container. Space is part of the dynamics. It's part of what's happening. Fields fill space. Particles are excitations of those fields. The fields interact. The interactions create forces. The forces affect motion. Motion affects fields. It's all connected. You can't separate space from the stuff in it. You can't talk about empty space in isolation because space is made of fields, and fields are never truly empty. They're always fluctuating, always creating virtual particles, always participating in physics. This is a radical departure from how people thought about space before quantum mechanics. Before, space was just coordinates, just a way to label where things are. But now, space is physical. It has properties. It has energy. It has structure. And that structure is quantum. This changes everything. It changes how we think about the universe, how we think about what exists, how we think about reality itself. And we owe much of this understanding to Richard Feynman and the other pioneers of quantum field theory who showed us that space is not what it seems. I know this is hard to accept. I know it challenges every intuition you have. But that's the point. Reality at the quantum level is not intuitive. It can't be visualized with classical pictures. You have to let go of the idea that particles are little balls. Let go of the idea that space is empty. Let go of the idea that things have definite properties before you measure them. These classical ideas are wrong. They work well enough for everyday life, but they're not the truth. The truth is quantum. The truth is fields and fluctuations and superpositions and entanglement. The truth is strange. And Feynman's explanation is terrifying because it forces us to confront this strangeness. It forces us to admit that we don't really understand. That we can calculate, but we can't visualize. That we can predict, but we can't intuitively grasp. That the universe is built on principles that violate common sense. And there's no escape from this. We can't go back to classical physics. We know it's wrong. Experiments have proven it wrong over and over. Quantum mechanics is correct. Weird as it is, it's how nature actually works. So what do we do with this knowledge? We accept it. We study it. We use it. We build technologies based on it. Semiconductors, lasers, MRI machines, atomic clocks, quantum computers. All of them rely on quantum mechanics. All of them work because we understand the quantum nature of space and matter. We might not understand it intuitively, but we understand it mathematically. And that's enough to harness it, to use it, to build our modern world on top of it. And we push forward. We ask new questions. We design new experiments. We test quantum mechanics in new regimes. We look for places where it might break down, where new physics might emerge. We explore the Planck scale. We study black holes. We search for quantum gravity. We're not done. We're nowhere near done. The quantum nature of space raises as many questions as it answers, and those questions are what drive physics forward. They're what make this exciting. They're what keep us searching. Richard Feynman showed us the way. He showed us how to think about quantum space, how to calculate with it, how to test it, how to accept its strangeness without giving up on understanding. He didn't have all the answers. Nobody does. But he had the right attitude. Curiosity, skepticism, honesty, willingness to say, I don't know, willingness to try new things, willingness to question everything, including his own ideas. That's the scientific spirit. And that's what we need to keep exploring the quantum universe. Space is not what you think it is. It's quantum. It's full. It's active. It's strange. And thanks to Feynman and others like him, we're beginning to understand just how strange it really is. This is the universe we live in, and it's more wonderful and more terrifying than anyone imagined.